Some of the elements in Group 13 and 14 have been at the forefront of scientific research and development over the past decade. Of particular note are the elements boron and aluminum from Group 13 and 14 respectively. Group 13's boron can bond with nitrogen to form boron nitride, a compound that is highly thermostable and is capable of resisting decomposition from pressure-based, heat-based, and chemical-based decomposition, all the while retaining its initial strength and form even at very high temperatures. While it has many crystal structures, the most prominent among them is its hexagonal form. One research in particular cites the usefulness of hexagonal boron nitride in photonics. First, let us discuss what is photonics. In case many of you are not familiar, photonics governs the physical science of light, particle detection, generation, and manipulation. Study goes broader than just physical sciences, of course, since it has application that is most useful for telecommunications, such as fiber optics, and electronics and consumer equipment like scanners, just to name a few. The study published in Nature Scientific Journal by Caldwell and his colleagues showed the potential of hexagonal boron nitride in the field of nanophotonics, especially for use in infrared level on chip photonics and hyperlensing. In addition to their use in this field, Caldwell and his colleagues also attested to the tailorability of hexagonal boron nitride, which can give way to future applications. Despite its usefulness, however, hexagonal boron nitride is still a work in progress. Plenty of research and improvements are still needed to make it a practical technology. As we have discussed earlier, silicon has an array of applications in the field of electronics. One of silicon's potential uses in or applications is in quantum dots. Quantum dots are basically tiny man-made crystals that can generate colors when exposed to specific spectrums of light. More specifically, quantum dots are nanoparticles that can transport electrons upon exposure to ultraviolet light. The colors emitted and absorbed by these nanoparticles can be fine-tuned based on the relative sizes of the particles alone. Coupled with its tailorable composition, shape, and structure, quantum dots can be used for a vast range of applications, the most prominent of which is bioanalytics, wherein these particles are employed for tracing specific metabolites and their progression in the body. The image above portrays several vials of quantum dots as they are exposed to a specific wavelength of light. A study published in the Frontiers in Chemistry journal by Morozova and her colleagues showed that progress of silicon quantum dot development rather, over the past decade. Their study highlighted the biological and environmental impacts associated with using quantum dots made of other elements such as the group 3, 3b, 3a, mostly the transition metals, as well as its potential as a limiting light-emitting diode, or LED. In addition, Morozova and their colleagues also highlighted key aspects that can be optimized, such as the efficiency of photon emission to make the technology more efficient or optimal and practical. Like the hexagonal boron nitrides that have been discussed previously, silicon quantum dots still require plenty of work to make them very efficient. This concludes my presentation. Thank you for listening.